Hello everyone, I am Subin Kim and I am going to start my presentation of 2021 Spring CS350 midterm. This is the honor code of midterm. I hereby swear that the work done on this exam is my own and I have not given nor received aid that is inappropriate for this exam. I understand that by the school code, violation of these principles will lead to a significant and strong penalty. Now I will explain problem 1. Boeing 737 MAX had two crashes in October 2018 and January 2019, and a total of 346 people died. 737 MAX was a modified version of 737 NG, and Boeing deployed MCAS rather than redesigning the plane, even though 737 MAX had bigger engine than 737 NG. MCAS is a Maneuvering Characteristics Augmentation System, which is a computerized flight control system. Also, one of the angle of attack air sensors were vulnerable to failure. Pilots were given only a short time to recognize and respond to the faulty data from these sensors. The 737 MAX operations manual did not notify the short response time. In perspective of 4Cs, which is cost, communication, change, and complexity, Boeing sacrificed communication and change to save cost, while complexity stayed the same or increased. Boeing had several reasons to care about cost. There are four reasons introduced in Boeing's 737 MAX: a failure of management, not just technology. In 1997, Boeing merged with McDonnell Douglas, which was a smaller aircraft maker that focused much on cost rather than safety. Also, Boeing moved the headquarters in 2001, which created physical distance between the leadership of the company and the technical teams focused on the 737 series. The European consortium Airbus, that was founded in 1970, was also closing in on Boeing, and Boeing was pressured to make more cost-efficient products compared to Airbus, which was funded by the European consortium. Finally, in 2005, CEO Muhlenberg carried his former CEO's strategy of putting marketing and cost before expertise in techniques and safety. These multiple situations led to Boeing caring more about cost than safety. Compared to the cost, communication was less prioritized. In 2014, pilots experienced on earlier 737 models could fly 737 MAX without new training. In 2016, Boeing allowed test pilots to stop flying actual 737 MAX planes and use flight simulators. Also, changes about MCAS, which had a short response time for faulty data, was not notified in operations documentation. 80% of 737 MAX planes shipped without AOA disagree alert due to lack of information in operations manual. This all led to immature response of pilots when AOA air sensor broke before the crash. Complexity-wise, 737 MAX also had bigger, more fuel-efficient engines than 737 NG, which is the former model. Changes should have been made properly according to the changes from the 737 NG to 737 MAX. However, Boeing deployed MCAS instead of new design for a heavier engine. Also, they used simulators that did not properly mimic 737 MAX behavior, which pilots relied to when they tested before actual flight. As mentioned before, one of AOA air sensor was faulty and cheaper than the other. Besides from the perspective of using 4Cs, we can also use the perspective from the given article why software fails. First, the inability to handle a project's complexity. Boeing did not consider the changes that occurred when launching 737 MAX from the former model. Second, the inaccurate estimates of needed resources. Boeing reduced investment in pilot training. Third, poor communications among customers, developers, and users. Boeing did not have enough operations documentation about MCAS, and pilots were not notified about faulty data. Fourth, there was piling commercial pressures. There was an intensifying competition from European consortium Airbus. Fifth, risks were unmanaged. The faulty data of AOA air sensors were not handled. Sixth, Boeing used immature technology where simulators did not duplicate the actual plane behavior precisely. Last but not least, one of the AOA air sensor was vulnerable to malfunctioning, which indicates sloppy development practices. Then, how can we prevent such accidents like Boeing in the future? We should put safety before cost and invest for test flight on real planes rather than using simulators. Also, we should not implement immature technology. Instead, we should redesign according to the engines and devices. During the process, we should not overlook even the smallest errors. Note any potential threats to pilots and write the operations document as specific as possible. Through these things, we can hope for a safer and better plane in the future. Next is the second problem. If we have to choose a more dominant entity between complexity and change, then complexity is more dominant over change. When a software is complex, it is more error-prone and more likely to have technical debt. This will cause a lot of debugging and fixing in the period of maintenance. Also, a lot of changes should be made if one wants to change even the simplest features in a complex software. High complexity also causes lots of communication. For instance, Google is one of the most complex software, and to manage Google, workers in Google company uses diverse communication tools to communicate effectively. Compared to the amount of total communication the Google workers go through, total communication in smaller applications is less in amount. On the other hand, even if Google company has effective communication, it doesn't mean that the system of Google can reduce in its complexity. A big software such as Google must have complexity exceeding certain minimum complexity. Below is an interesting quote about the effect of complexity referenced from Managing Technical Debt in Software Reliant System by Brown Nunnett et al. Increasing complexity makes system rigid, hard to change, fragile. Each change breaks something else, vicious. Doing something right is harder and opaque, hard to understand. Also, because of technical debt, if complexity is high, cost may likely to increase. Below is the graph that shows the proportional growth of maintenance cost to the features of application. Communication affects cost as well. If there is effective communication, it can reduce the human labor cost of figuring out other developer or designer's intentions and codes. The quote from the role of software processes and communication in offshore software development supplements this. It says, communication and coordination mechanisms in offshore development reduce project uncertainty and improve performance. Effective for V3, waiting only on messages from P4 and P6, vice versa for B4. Petronet B is more likely to be fault-tolerant than A. For instance, if message from P4 matches the message from P6, B may not catch the error in P6, and V2 will fire normally. However, in A, P1 has to wait for all three messages in P1, P2, P3 before firing. If P1 and P2 matches, but P3 has an error, system following A will catch the error. The Petronets A and B may suffer from imprecise representation because they did not specify a selection policy, which is 2 out of 3 voting policy in this problem. This may lead to confusion when implementing these systems depicted in Petronets to real systems. Now, I will move on to problem 4. Problem 4 was answered according to the reference in the link below. To estimate use case points, first, we have to estimate unadjusted use case weight. I classified 13 use cases from the given use case diagram in designing and implementing of ATM system using object-oriented approach. I categorized the use cases to simple, average, complex, following the criteria given in the reference link. The simple cases are inside the yellow box, the average cases are inside the green box, and the complex cases are inside the blue box. I counted one block as one transaction in the activity diagram given in the article. Invalid PIN, system startup, and system shutdown are simple use cases, which have 1 to 3 transactions. Activity diagrams of system startup and system shutdown were not given, but the transactions of putting on and off powers to the ATM would be less than 3. The use cases of managers and officers are average use cases. Each use case passes 6 transactions. When the information for validation in the third transaction is insufficient, the ATM machine shows message to the officer or manager, which still passes 4 transactions and categorized as average use case. Balance inquiry in the use case of customers is also average use case, which will be explained in the next slide. The use cases cash withdraw, deposit, and transfer are complex use cases. I included the session use case to count transactions use cases, which uses credit card and PIN to validate the user and shown in Figure 2. This is because to use the customer transactions use case, the customer must necessarily pass the sessions use case. Hence, additional for transactions is added to each customer transactions use cases. Next, we should calculate the unadjusted actor rate. I decided that the bank was an average actor because the ATM communicated with the bank to get approval of PIN number when starting the session use case and verifying balance during transactions use case. The rest of the actors are human actors, hence complex actors. This is the technical complexity factor. I wrote the scores and the reason why I graded the score. I will not comment on these details. This is the environmental complexity factor. I wrote the scores and the reason why I graded the score. I will not comment on the details. The final user case points can be calculated as 122.22. The formula is in the given reference link. Separation of concern is used in the use case points estimation. When we calculate UCP, we separate it to 4 different criteria, which is UUCW, UAW, TCF, ECF, and mix them to get the final result. This is separating the concerns for judging whether the use cases are well defined and well used. This is the end of my presentation for 2021 Spring CS350 midterm. I put in a lot of effort, and I hope I can get a score proportional to my efforts. Thank you for listening to the presentation.